Here we have okay, so we have a given transfer function. S of s is equal to 4 over s times s plus 2 squared. And then we are going to use the partial pressure expansion. Okay, so how do we determine the coefficients? A and B and C. Now, for the A is easy, right? So let's multiply the entire function. Right? S. And then we take the limit. We let S approach 0. Now, if we look at the right-hand side, we can see the dimension. Okay. Now, this S will cancel out the S in the denominator for the first term. So we have only A left. The remaining terms are common. Okay. So this is the A. And what about the B and C? Okay, one of you proposed to find the C, right? Would you write down that for me? Okay, so we can find the C coefficient C. Okay, now be careful here. You need to take limit, right? You need to take limit on the two terms. Okay, but yeah. Okay, good, thank you. So by multiplying s plus 2 squared on both sides of the equation, we are able to determine the C. Okay, so now C is being found. A is being found. How to find the B? How to find the B? And we tried that last time. If I multiply the entire equation by s plus 2 only, okay? Then we have a problem. We have a problem on the third term. Right? The left-hand side and the right-hand side now is, okay, this is 0, that's 5. And then plus B, and then C over S plus 2. But then we have to keep the middle. That's the closest negative 2. We have a problem here, right? So this is not all. So instead, what can we do here? One of the approach is given by the book or some other books. Okay, if we let, sorry. So now if we let S be, say, 1, for example. Okay, so the XRS is equal to A over S, and then B over S plus 2, and C over S plus 2 squared. And likewise, we let S be 1. So we have the left-hand side now is 4 over 1 times 1 plus 2 squared. The right-hand side is A over 1, and then B over 3, and C over 3 cubic, that's 9. Since we have found A and the C on the previous 2 steps, so we are able to determine the B coefficient. So B equals to 4 over 9 minus A minus C over 9. Okay, and then multiply by 3. That's one way to do that. That's fine. Okay, that's fine. But there is another method. So let me go this method number 1. So this equal whatever the number is. No big deal, right? But there's another method. Okay, again, let me repeat here's the function one more time. Now, which is quite similar to the method proposed by your classmate, which is very similar. So let's multiply the entire equality by S plus 2 squared. Okay, let's do it. So that's equal to A over S times S plus 2 squared, and then B times S plus 2, and then C. Okay? Now think about this. Is there any method I can find B coefficient? And in the meantime, I also can get rid of A and C. What should I do? The idea is to find B coefficient, right? Coefficient B, but we don't want A and C at the same time. So any suggestion, we can do that. A very not so simple, but simple, yeah, kind of simple trick. Then we are able to find B without involving A and C. Any idea? Come on, engineers. Software software engineer, okay, and aerospace engineer. Come on, computer science, aerospace. Come on. It's a trick, okay? But you can figure that out. One more time. Do it. Oh, I forgot to multiply, sorry. Multiply. This part is still here. And keep going. That's fine, just tell everyone your idea, okay? Yeah, I think that's good enough. We don't have to finish the main step. That's good enough. Okay, now here is the idea proposed by your council. We multiply the entire quantity by s plus 2 squared. Then we have this one on the left side, on the right hand side. How do I derive the parameter or coefficient A and C, and also leave the B intact and affected? We simply differentiate the entire quantity with respect to S. Okay? And then we let S approach magnitude again. See what happens. Okay, so let's go back to this step there. So the left hand side is limit. S approaches magnitude, and then we differentiate the coefficient over S. I'm sorry, the function over S. Okay, and then the right hand side, we have A times d over dx. S plus 2 squared over S. And then plus B times d over dx. S plus 2. Then C this term disappear. Okay, now this one is easy, right? We have 4 and negative. That's negative 2. This equals to, this approaches to negative 2. And then, what about this? Sorry, I have to take the negative, okay? A times limit s approaches negative 2. Okay, and minus b times the limit s approaches negative 2. So what's this thing? This is a times the limit s approaches negative 2. What is the differentiation of this thing? Okay, you have e over ds, 1 over s, times s plus 2 squared. And then 1 over s times e over ds of s plus 2 squared. Now, no matter what this differentiation is, but it's multiplied by s plus 2 squared. And then we let s approach negative 2, so eventually this will disappear after taking the limit. Right? What about second term? Again, this is s plus 2 squared. Differentiate with respect to s. So this is equal to 2 times s plus 2. So again, if I let s approach negative 2, this will disappear. Again. So both terms are not. Okay? So the first term eventually is 0. And then the second term is simply b, coefficient b. The third term is already 0. So we are fine. Okay? So we are fine. So the b is equal to 4 times 1 over negative 2 squared with minus sign here. That's negative 1. Okay? So this is another method to find a coefficient. And I have to say that nothing is free. Nothing is free. This method proposed by the textbook looks easy, but it's only for simple functions. Okay? If you have more than 3 or 2 parameters, you have lots of parameters. You have to solve equations simultaneously. It's not easy. It's not easy. And similarly for this method, it's also not so easy. If you have a high order system, you have to compute those derivatives. Okay? So again, nothing is free. No free lunch. But those are methods. You also may find some other methods from some other papers or some other books. Okay? Alright, so any question for this one? If you have no question, then I think last time I did not solve the equation, solve the differential equations completely. Let me finish that first, and then let's move to the next chapter. Okay, last time I only solved part of this differential equation. Okay, so let me finish it. Okay, I've done the first one. The second one, suppose the initial value of I0 is non-zero. Okay, so the initial value Okay, 0 minus. That's fine. Okay, again, let's make the Laplace transform of the differential equation first. Now, since Laplace transform is a linear operator, so I can split the operator, the transform, and also figure out the constant. Okay, and then apply the property of Laplace transform. The first term, the Laplace transform of the I over dt, we have two terms, I of s minus the initial value. I think last time I did a mistake here, okay, so please correct the mistake. R times the Laplace transform of L t, then you correct L s, I of s. And then this is the piece of this of s. Okay? Okay, now compare with the case number 1. Here we include the initial value. So we have L times L minus L times x into the initial value. And then plus R times L equals piece of this. Okay? Where L is by definition the Laplace transform of T, and then the piece of this of x, which is the Laplace transform of the time function, the input control voltage. Okay, so now we can collect the terms involving L's. So I have, oops, sorry, okay, I missed this, sorry. S times I have S, sorry. S times L. Okay. S is the differentiation in the time domain. So we have Ls plus R times Ls equals this minus of x plus L times that of 0. So the Laplace transform of the curve is given by 1 over s plus R. Okay, and then times the this minus of s plus 1 over s plus R times the initial value, nice of 0. So that's the Laplace transform of the curve in the circuit. Okay, so the time response, IL3 is simply the inverse Laplace transform of balance. So in this case, it will be the inverse Laplace transform of 1 over ls plus r times e sub s plus, and then plus the inverse Laplace transform of IL0 over ls plus r. Okay? Again, I think last time I did a mistake here, so please make the correction. Okay. Alright, now if the input is at s of t, the control voltage is a unit step u of t, and for t is bigger than or equal to So E of t equals to 1. When t is greater than or equals to 0, right? And otherwise, it's 0. That's U of t. The I of t is equal to, what's me? So E is this. What is the Laplace transform of the unit step? One over x. We have to memorize that. Okay? So the I of t now is the combination of two terms. That's the first term. Okay? And the second term. Alright, so now we have to go to the quadratic expansion again. So 1 over s plus r times 1 over s. And we read this the combination, the partial bracket expansion, a over s plus b over s plus r. Okay? And how do I find the a, coefficient a? To determine a, okay, for the a, yeah. We take the negative. S approaches 0. And then r s plus r times s. That's equal to the limit. S approaches 0. A over s plus b over s plus r times s. And that's the right hand side. And that's equal to a plus. Okay? And this is s times b over s plus r plus 0. So equals a again. So now we replace s by 0. So the left hand side is simply 1 over r. And left hand side 1 over r. Okay, s is 0. And then the a is done. Okay? And then for the b, similarly, we let this approach to negative. Okay? All the way up. Okay? And then 1 over s plus r times this. And the s plus r. That's the left hand side. And the right hand side, that's b. Okay? So the left hand side is simply negative all the way up. And it's so hot. And the right hand side is only the b coefficient. So we have both a and b. Okay? So now we are able to determine the I of t. I of t is the inverse. The function of a, which is 1 over r times 1 over s. And then plus inverse of the transform of b over the s plus r. And that is negative r over l times 1 over s plus r. Okay. Okay, so that's equal to 1 over r times the inverse Laplace transform of 1 over s, which is the unit step. Okay. And then this is equal to negative r over l times this guy. Okay. Let me open the side here. The inverse Laplace transform of s plus r. So let's divide through by l. Repeat something here. Well, I think that is, so over L, and then the inverse Laplace transform is from e to the negative over L times b. So it's a combination of two terms. Okay, for the first, on this, let's start from the input. This is input response. Let me do this again, okay? This is I over P input response. Controls, okay, IC of P, control. So then you go to IC of P is equal to this one. And then we have another one, let me call this the initial value, I sub L P due to initial value, okay? So this is equal to 1 over L again, and then times the initial value, and then times the inverse Laplace transform. Okay, so that's equal to y sub 0 over L times e to the negative over L times b. Okay, right. All right, so the sum. Eventually, ILP is equal to the sum of the above two functions, I sub 0 p due to the controls input, and this is still the initial condition. Okay. Our major point here is how do we implement the partial fraction expansion to determine the coefficients? That's a major point in this chapter, in this section, in this section, okay? Any question? Any question here? Now, from the response, from the time function, you can see that there one more comment here. The I sub COT involves two terms. This is unit step, and this is exponentially decay. Okay? This is exponentially decay. So when t approaches small amount here, okay, before we finish this. So when we take the limit, one is we are considering the steady state. Okay, when we take the limit, then look at the I sub CLT, there are two terms. This one is unit step, so it is always equals to 1, and times 1 over r. And the second term, it is an exponentially decay. This is an exponential decay function, right? So it will decay. Eventually, it's going to approach to 0 after a long, long time. And similarly, for the initial value, okay, this is the output due to the initial value. Also, this is an exponentially decay function. So when t approaches a huge number, it's going to decay to 0 as well. So both these two terms go to 0 as t approaches infinity. Why we have this kind of good good result? Because this is a pole. Negative power value is a pole. And look at the transfer function here. This guy is the transfer function 1 over F plus r. This is the transfer function, really quite clear. Okay? Now, when Ls plus r equals 0, the S is equal to negative r over L. That's the pole. This is the pole of the transfer function. And if we look at the location of the pole, it is on the, let me draw that here. Okay, let's consider this pen. This is the real axis. This is the imaginary axis. This is equal to negative r over L, so somewhere over here. It's on the negative real axis, as we have mentioned that the response of this one is exponentially decay, right? So this is a stable pole. This is a stable pole. Okay? So that's why eventually these terms, they all disappear. They die out after the time elapsed a huge long term later. So only the first one survives. And this is a steady state response of the system, of this system. So this is the steady state response. Okay? All right, we will see that later. Okay, again. Just give you a taste, a very simple explanation here. Okay? All right, so that concludes chapter number 3 here. Okay, for a long time. That's been quite a long time. Okay? Any question? By the way, any question again before we move on to the next part? Oh, one more point here. When you were deriving the final value theorem, remember the theorem we could prove, right? The steady state value is the final value theorem, actually. Okay? So this is the final value, the terminal value. When t approaches infinity, only this term survives. That's 1 over r. The number is 1 over r. Okay? So this is the terminal value, the final value. So number 1, number 2, the limit. T goes to infinity. Okay? Or L T, that is equal to the limit. S times Ls. And this goes to where? Goes to 0. Right? Okay? And that is equal to, if you multiply Ls by S, and let S approaches 0, you have 1 over r left. That is equal to the limit. S approaches 0, and then S over S, S plus 1 times, in this case, this is 1 over S, right? And then times the, and then times S. So this term disappears. Only this term survives. That's 1 over S. So this is the steady state value, the terminal value, 1 over r. So actually, the final value theorem is to determine the coefficient of the step response. That's it. Okay, physically, let me repeat that again. The final value theorem, or sometimes it's called terminal value theorem, is trying to determine the unit step response, the coefficient of the unit step response. That's it. Period. Okay? That's the physical meaning of the physical terminal value or final value theorem. Okay? Alright, so that concludes the chapter number 3, and let's move on to chapter number 4. That's the final value theorem. And by the way, I think last time you have let me just remind you again. Give me 1 minute. last week or the week before last week, I had asked you to run a program, right? Run those MATLAB program. Now, which means actually we also can use any commercial package like MATLAB to compute the coefficient in the partial fraction expansion, in the B and the C and whatever. Okay? So nowadays people use commercial package to determine the partial extension for transfer functions or the Laplace transform of signals. Okay? So we seldom use the hand to compute those coefficients anymore. Okay? But you still have to know. You still have to know why and how, because sometimes the commercial package they also did a mistake. You have to have the ability to detect that mistake and also make the correction. Okay? Those software, even though it's very powerful, they also were written by human beings. They are not written by God. Okay? So don't tell me one method can do that 100% correct. Wrong. Personally, I have found many bugs in MATLAB reported to the MATLAB networks. Okay? So they did mistakes too. And you also have to figure out, also you have to be able to detect whether the given solution is correct or not. That's very important. Okay? So please do not trust the result or solutions given by the software computer. It is very dangerous to do that. Okay? All right, let's take the 10 minutes break, and then we'll start the new